This section's 9.7 in 9.10. Taylor series, Maclaurin series, and Taylor polynomials. These two sections are separate sections in the textbook, but I think they are actually pretty much the same. So I'm going to combine that into one section under one PowerPoint slide, technically. All right, so let's recall. In these sections, we've been learning how to test a series whether it converges or diverges. Now, throughout the first 6-7 sections or so, we've done a lot of testing, but you probably have no idea why we're doing what we asked to do, right? So the reason is all of these is a little bit behind the scenes when it's come to the calculus materials, a lot of things, the theorems, what's behind. So this is more like what behind all those theorems, and so it's hard for you to see the connection to the real world application. Okay, so that's why this chapter is a bit boring. It's more like mechanics you do, and then you don't know why we do that. Now, when we come to these sections, we will have a bit of connection here. So I'm going to show you a little bit why we like to check whether the series is convergent or not. Now, first of all, after we learn all of these, and then we learn the power series in 9.8, the main objective, in fact, in this chapter is not testing series. It's just part of it. But the main objective is we would want to represent A functions by a series or a polynomial. Okay, so what do I mean by that? If you have a functions, now in reality we have lots of functions that is very complicated, by the way, but I'll just write some function that's not that complicated, so it's still very simple. Let's say it's just an e to the x functions, okay, or the functions of the sine and cosine. Now notice that even though these you think it's simple, but when it's come to, let's say, solving equations, if I give you a very easy one, so e to the x minus in cosine of x, right, equal x, can you solve this equation? You see, this is not an elementary equations where we don't have really technique to figure out the solution to the equation. So if and somehow we can write these functions, we call these are really transcendental functions. We want to write these functions using a different functions. We call that as approximations. So let's say if the function e to x, somehow we know it's approximately, or it's gonna be about 1 plus x squared over 2 plus x cubed over 3. All right. Now, these two functions, of course, are not the same. But you grab this exponential function. This is a third-degree polynomial. Now, right around the origins, if you grab them, you might see, well, they are pretty close, okay? So that means if you plug the values here on the left and the values on the right, and they are about the same values, so we can use the right-hand function or the third-degree polynomial functions to approximate the value of these functions. And then if you're going to solve the equation, right, so if you replace this with this, you see that's a lot easier. This is a polynomial third degree, so it's much easier to solve. Okay. Then if we're able to find such functions, in this case, we call this polynomial, the third degree, right? This gonna have the name later called as Taylor polynomials. Okay. So the goal is, how do I know if I'm given the functions, there is a polynomial that will be equivalent to or really close to this function that we can use. Okay, so or essentially we're going to find a series. If that's going on forever, then we might be able to find a series that is exactly these functions. All right, so a bit weird, but yes, we could find a series that is equivalent to this functions. Okay, and then we're going to use that information, this series, to do lots of things. Okay, instead of use this function, we're going to dealing with this series, and that series is called the Taylor series. Okay, so on another note, you might not know, or maybe you might know, for example, 3 is a number, right? Some integers, but this is really the same as the series of the decimal numbers. Point is 2.9999, let it go forever. Okay, so 3 is the same as that number. Now in this case, of course, it isn't. No, I don't prefer this. But here we're going to prefer a series over a function, okay? Because that is really a better way to deal with the series than the original function, okay? So now, how are we going to do that? Okay, so that's the question. How are we going to do that? Now, one thing, let me do this in general. So let's say if you have the functions, okay, so if you have the functions as x, and then you want to find a series, okay, or a polynomials, okay. So let's say the series, the power series, I'm talking the power series, right? So the power series we call is the one that looking like this, the a sub n, right? X minus c to the n power, and from from 0 to infinity. Okay, so if you write out explicitly in the expanded form, it will be a 0 and x minus c to 0 is 1, plus this next term you have a1, and then x minus c to the first plus a 2, and okay, 2, and then you have x minus c to the second power plus a 3, and x minus c to the third power, and so on. Now, if there is such function exists, I mean the series equal to the original function we want to find or represent, then if you look at this side, the power series always has that form, right? So it's always that form. And the thing is, we need to figure out these coefficients, A0, A1, A2, A3, okay? Now, let's check it out. Let's say if they are equal, right? So if I plug in, let's say if I plug in C into both sides of this equation, right? If you plug C into this function, f of C, plug C in here, then you're going to plug C in here, right? So what you get, this is a naught. Don't forget that C minus C is 0, right? It's 0. This is 0 squared, so it's time anything 0. So you have a whole bunch of 0. So you see that you plug 0 in you'd actually end up with f of c is a naught. So that means the constant term of this series is really by plugging the c into the original function. Now, if we're going to take the derivative, okay, let's take the derivative of this function here. F prime of x, right? So there's a constant, derivative constant is 0. Derivative of this, well, x minus c, derivative x minus c is 1. So it's really a 1 times 1. Now, derivative of this, you bring the 2 down, it's gonna be 2 times h1 times x minus c, right? Then that one, you're gonna have 3 times a3 times x minus c squared, and so on. Now, notice that here we have this where every single term has this x minus c quantity, except for the first one, right? So again, if I plug c in, right? So if I plug c into this equation, so f prime of c, then you do have 2 times, not 2 times a1 plus what you get here, c minus c 0, so that's gone, right? 0, that's gone, 0, so the rest is 0. So what you see is now f prime of c is really a1. That is the coefficients of this one. a1 is really f prime of c. Okay, you see that? All right, so I could continue this, and then you should see a pattern. As I'm going with the second derivative of the functions, then taking the derivative of that, you see this is constant is gone. So now this has become is a 1, so you have 2 times a1 there, and then plus derivative this one, 2 times 3 is 6. I'm going to write 2 times 3 instead of 6, it'll be 2 times 3, a3, and that's x minus c to the first power, and then continue. Now the rest, because the power now is 3 and 4 and 5, so see that they're gonna have the x minus c survive, right? So if you plug in the derivative at c, then you see all of them 0. Now you're left with 2 times a1, and therefore not a1, I think I got this wrong. It's sorry, that one's a2 here. That's a2, it's a2. So now we have f prime of c. If you divide by 2, then you got h2. Now you can see we can figure out quickly h of 0 is f of c, and that is f prime of c. That is f double prime of c, the second derivative, divided by 2. Now, if you continue on, the next derivative is the third derivative, so I expect that to be the third derivative, right? So if you do the third derivative, here again, a constant 0, and then you have 2 times 3 times a3, and that is 1, and then the rest. But if you plug in, you can see that the rest will be plug in c, the rest will be 0, and except for 2 times 3 times a3. Now notice that the living 2 times 2 instead of 6 is because now the bottoms, if you solve for a3, you're going to see it's triple prime of of c over 2 times 3. That's 3. So to make it look like a pattern, this really a 1 there divided by 1. That's really 1 times 2. This is 1 times 2 times 3. Because the derivative you keep taking, then bring it the highest power. The next one you're going to have 1 times 2 times 3 times 4. So the bottom is really 1 factorial, 2 factorial, and 3 factorials, and so on. So the next one, if you're going to find a 4, you can guess, well, that's going to be a fourth derivative at c over 1 times 2 times 3 times 4, or 4 factorial. Right? So now you can say we will always be able to find a series that represent these functions where this coefficient could be determined by this formula. That leads to the following theorems. If f of x is represented by a power series of this form, for all x in the open interval I containing the c. Okay, c is a constant or the center of the series. Then the a sub n, that formula there is that coefficient a sub n could be calculated by the nth derivative evaluated at c divided by n factorial. Like it over here. All right. Now, if you plug this back, right, a sub 0, you plug in here, f of c, here a1 f prime of c, and here's f double prime of c over 2 factorial. Here's f triple prime of c over 3 factorial. If you plug it back, we now have a complete formula to the series that we use to represent this given functions. And this series has a special name called Taylor series, center at C. So that leads to the follow definitions. Right, so definitions. The series of the form, see the series of the form, this, now it's really the same up here. I just plug in the formula for a sub n in here. So you're gonna got f of c and f prime of c over 1 factorial, x minus c, etc. And this is called the Taylor series for f of x at c. Now notice it, even though at first it might look very complicated, but it's very easy to even memorize it because all the n derivative, power, and factorial, they all match up. See, that's third derivative, third power, sorry, second derivative, second power, 2 factorial. Third derivative, third power, 3 factorial. So they really match the power, derivative, in the number at the bottom. Now, in the special case, when c equal 0, then the series is called the Maclaurin series. So when I specify the Taylor series, I will have to tell where is the center, right? So I need to know, is it x minus 2, x minus 3, or x minus 0? If it's x minus 0, then we say that is a Maclaurin series. All right, so let's take a look at an example 1 here. Find the Taylor series for the functions y equal cosine of x, center at x equal pi half. At x equal pi half. Okay, so according to the theorems here, of the definition, you see all we need is to figure out the values of the function at c, then at the derivative, first derivative at c, second derivative at c, third derivative at c. The rest is always the same, right? So 1 factorial, 2 factorial, 3 factorial, bottom are the same. No matter what function we're dealing with. The only thing that changed is the function's values, first derivative, second derivative, third derivative at c. So we're going to start with, in order to fill out the information for the Taylor series, we start the function f of x cosine x, right? Here's the c. You plug pi half in, right? Cosine of pi half. Cosine of pi half is 0, right? Plug cosine pi half is 0. Then I take the first derivative. Derivative cosine is negative sine. Then plug pi half in. Sine of pi half is 1. So with the negative, it's negative 1. Second derivative. Derivative sine is cosine. The negative. Plug pi half in. I think we get 0 again. Now the third derivative. Derivative cosine is negative sine. With the negative, become positive sine. Plug pi half in. It's 1. Continue. The fourth derivative. Derivative sine is cosine. Plug pi half in. 0. Continue. Well, we don't have to continue. So technically, when do we stop? Right. So we should go on forever because it's an infinite series. So long as we are able to see the pattern, that is, I can figure out the next one is the fifth derivative pi half here without doing the actual derivative. You see that because the fourth derivative back to the original function, so there's a cycle of 4 there. And you can see the coefficient go from 1, negative 1, 0, 1, 0, so back to here. So it'll be 0, negative 1, 0, 1, 0, negative 1, 0, 1, and so on. Now put it together. You see I have x minus pi half to the first, that's a constant, right? That's to the first, that's a second, that's a third. The denominator is the same always, right? That's 1 factorial, that's 2 factorial, that's 3 factorial. All you need is put in, it's a 0 for the constant, it's a negative 1, it's a 0, it's a 1, and 0, 1, and the next one will be 0. Okay, now as you plug in, you should see this gone, oh 0, so this thing's gone. So basically every other term got dropped out because the coefficient is 0. And so we're left with just the odd powers of the x minus pi half. So this is the first. You're going to see that it'll be the third. So the next one is the 5 should be the fifth. And don't forget it to be the fifth. Then the coefficient now will be negative 1, and the denominator will be 5 factorial. And we end up with this series, Taylor series. Negative, so that third power to over 3 factorial, fifth power to the 5 factorial. The next one should be raised to 7 power over 7 factorial, and the sign actually alternating. So we actually end up with an alternating series. Alternating series. Now, this is what we're going to write in the expanded form. But how do we write it in the sigma notation? So you might be asked to do so, right? So if you put it in the sigma notations, then this will be equal sum. Okay. Now, This is something you might have to remember. The power is all odd. Okay, so when you have an odd powers, how do you gonna write it? It will be okay. Odd. We have the formula is 2n plus 1. Right? When you plug 1 in, you got 3. When you 3 in, you got 5. When 5 in, you got 7. So the odd number is 2n. If you have even powers, it'll be 2n. Okay, so because all of them is 1, 3, 5, 7, so the formula here should be x minus pi half raised to the 2n plus 1 power. Okay, 2n plus 1 power and divided by, you see the same, that's 1 factorial, 3 factorial, 5 factorial. So the bottom should be 2n plus 1 quantity factorial. And started with the Taylor series, we should have n start with 0. You can check at 0, you're going to have the first powers of that term. When n is 1, you got 3, so that term. Now the other thing is missing is you see the sign alternating -1, 1, -1, 1. So if you need that, you're gonna have the -1 to the that one's a bit tricky. Normally is n, but when you have n, you plug in, you have the positive 1 term first. But I start with the -1. So you're gonna have to add ones there. Okay, so we need some space. So it is -1 to the n plus 1 time, right? 1 and 0 to infinity. So that is a formula for this Taylor series. All right, sorry for the function cosine. So this is the Taylor series for this function cosine. Okay. Now let's take a quick look from the graph perspective. Now, remember what I told you is the function that the series that I come up with I use to approximate these functions. That when we say the series, it's to use a series to represent these functions. So what it means is the series that I have down here is going to be equivalent to the cosine x. So let's check it out from the graph point of view. Why do I say they are equivalent? Now, if you have fx equal cosine x, right? Well, that is not a good example. Or sorry, I'm gonna do a slightly different example here before I'm gonna show you the equivalent. The example 1 here, find Taylor series centered pi half. Now let's do the same function cosine x, but this time we're gonna find the Maclaurin series. I'm gonna verify this later. So Maclaurin series, again, by definition, is a Taylor series center at 0, right? So that means you're gonna plug in 0 instead of pi half, right? So the rest the same, right? Cosine x, plug 0 in. This time you got 1. First derivative, negative sign, plug 0 in, 0. Second derivative, negative cosine, plug 0 in, you got -1. Third derivative is sine, plug 0 in, you got 0. fourth derivative back to cosine, plug 0 in, you got 1. Now, the derivatives are the same, but now plug in 0 instead of I have, you get the series 1, 0, negative 1, 0, 1. So they again are the coefficient, which is the numerators of the Taylor series. So in this case, notice that I have just x instead of x minus 0. Remember the center is 0. So that is x minus 0 squared, x minus 0 cubed, x minus 0 4. So I don't write minus 0 there. The denominator, again, you see the 2 factorial, 2, 3 factorial, third power, 4 factorial, fourth power. The only thing we need to fill in is this number we got, starting at 1, then 0, then negative 1, then 0, then 1, right, repeating. And again, you see that the 0 terms here gone, and we left with the even. Oh, see, this is how interesting this one. This is the cosine x, the same functions with the series representing center 0. This time, what? The odd powers dropped out. We left with the even powers only. See, 1 is x squared. That's the next one, x to the 4th. Next one will be x to the 6th. Next one, x to the 8th. And you see the denominator is always matched up with the power. And the sign still alternating. Okay, it's alternating. Now I have this series, cosine of x equal 1 minus, then you see that it's all even power. All right, let's try to write that in the compact form. And when you write in compact form, look at the powers again. You see is 2, 4, 6, 8, 10, right? So there's an even power. So for the even power, you have x to the 2n. The bottom, it's going to be 2n factorial. Again, you're going to go from 0 to infinity. You can check by plugging 0. 0, you're going to got the 1. Then plug 1 in, you got this term. 2, you got this term. Except for the signs, again, alternating. You need the negative 1 to the n plus 1. No, not plus 1 in this case. I don't need the plus 1, right? And it's good. You plug 0 in, so you got positive 1. And then 1 in, you got negative 1. Yeah, so negative 1 to the n power this time. Okay. Now, again, I claim that these functions in this series are equal, right? So they're equal. Now let's check it out from the graph point of view. Now this is the cosine x, so you know, right? So it's going to oscillate between negative 1 and 1. Now, because this is a series with infinite many terms, technically it cannot graph the left-hand side. So what I could do is I'm going to graph the right-hand side by truncated certain number of terms. So on the left with really polynomials, okay? So let's say if you get rid of all the terms, and what I have left is the first term, okay? It's the first term, just 1. I'm going to write P sub 0. That means I'm going to get this polynomial of degree 0 is just a constant, right? And then I truncate the rest with the 2 terms left, these 2. Now, when the 2 terms left, this is really the second degree, 1 minus x squared over 2. So that is a second polynomial, right, P2. It's 1 minus x squared over 2, right? 2 factorial is 2. And then if you get rid of the rest and keep 3 terms, first 3 terms, I have a 4th degree polynomial we call the Taylor polynomial, by the way. The fourth degree Taylor polynomial is 1 minus x squared over 2 plus, and that's x to the fourth over 4 factorial is 24. And I keep doing that by keeping the first two, and then 3, then 4, then 5 terms. Then we end up with a Taylor polynomial of degree 0, degree 2, degree 4, degree 6. And I'm going to graph all of these comparing with the cosine x. And let's watch. The first one is the polynomial of degree 0, the constant function that is y equal 1. You see that the line and the cosine x, are they the same? No. But don't forget that we are looking at the centers, in this case Maclaurin series, center at 0. Right? So by that I mean if you look at the interval that close to the 0, where's the 0? 0 is right here. You look at the interval that's around 0, right? So you see the graph? These two, it's close. Okay. Now, if I continue and let's say I graph the P2, the parabola there. See, that's a parabola with this original cosine x. You see they actually close now. Well, it's even better the interval if I can increase the interval now to somewhere over here to here. You see that the graph of cosine and the parabola are almost identical, right? Then I consider the fourth degree polynomial. I graph it there. You see that? Now the graph of the fourth degree polynomials and then the cosine of x are identical from -2, about -2 to +2. And then go on, if I do a 6 degree, this, 8 degrees, 10 degrees, so on, right? So if when you keep writing more and more term, you see that the series on the right will converge to the cosine x. Okay. All right. So I guess this long video, I'm gonna stop right here for the first part.